Dear students, in this module, we'll look at one of the seminal algorithms that was developed to determine the stability of the 2' RNA structures. It is called the Zuker's algorithm. So given a 1' structure of an RNA molecule, you would like to predict the 2' structure. So for that, you would want to evaluate the overall stability of the molecule. Zuker's algorithm helps you to do that in a very simple way. Okay, the basic philosophy of this algorithm is that we would like to evaluate the free energy or the Gibbs energy that is available within the RNA 2' structure. You would remember that the little the Gibbs energy, the better. So if an RNA molecule has very little free energy, it will not be able to interact with other RNA molecules. So therefore, it will be more stable. Okay, so in Zuker's algorithm, which was reported in 2003, so what we have is 2 types of energy. The first one is the energy that is given out after 2 complementary nucleotides, they make a hydrogen bond. So this value is negative. Of course, if you have so many of these nucleotides that are complementary and are able to bind together, a lot of negative energy will be reported. So the net energy will be negative. However, as you know, there are some nucleotides that are not coupled. So what happens with them is that they contribute instability and therefore they add free energy to an RNA molecule. We denote them by a positive value. So you have a set of negative values and a set of positive values. The negative values are good, the positive values are bad. So therefore, you would want to have an overall negative value. So once you compute the sum, you can obtain the overall energy profile of a 2' structure. So the stacking energies of 2 nucleotides are given here. In case of A and U, it's minus 2.1 kilocalories per mole, and so on and so forth for all the 4 nucleotides. Similarly, you would want to look at the destabilizing energies. So they are given here by the type of the uncoupled nucleotides. In case these uncoupled nucleotides occur in an internal loop and the size is 4, then the positive energy is 1.7. Similarly, if they exist in a bulge of different size, then you can read off from the size of the bulge. And for the hairpin, as you know, a hairpin must have 3 or 4 nucleotides or more in its eye to form a hairpin. So if the eye has 3 uncoupled nucleotides, the energy profile will be raised by plus 5.6 kilocalories per mole. In this case, the overall sum will be a positive number. However, as you can see in the stacking energies, the energy profiles are negative. So essentially, you would want to have a negative value at the end of your 2' structure prediction. Negative value is what we want. More negative the value, the better. Please remember that. Okay, so given a sample structure, that is in this case, a hairpin loop, a helix, a hairpin loop, a helix, and some uncoupled nucleotides, you can simply look up the stacking energy for G and C, and this is what you will arrive at. Right? If you look at A and U, you'll arrive at these values, right? And the instability introduced by these molecules is written here. So essentially what you're now going to do is add them up. You must also note that as a result of these, the overall energy of the molecule is going down. That is good. Yeah, as a result of these uncoupled nucleotides, the energy is going up, which is bad, right? So you will add them up and arrive at a value for the entire structure. So in this case, you have computed the energy of the overall molecule, and you can do it for all the possible 2' combinations that can exist. Of course, you will go for selecting the RNA 2' structure with the lowest energy or a negative value.